So last thing for today is our exercise number 4. I think, to me, it's maybe not quite as much work as the last couple. We'll see. You've got a nasty equation to deal with putting into Python, so that's something that I've kind of factored in terms of the time. But I think the amount of work you have to do once you have the equations coded is not as much as maybe some of the previous weeks. So the exercise looks like this. It's about advection and diffusion of heat, as you might imagine. There is a problem 0 this week, and the problem 0 is basically to fill in a midterm course feedback form. This is something I pretty much always ask for in the courses that I'm teaching, just as a way to get some information about how things are going this year and about ideas for how things could be improved already still while the course is running, but also in the future. So if you go here to this e-form, you'll get something that looks like this with a couple just kind of general questions about how things are going, and then a numerical feedback about the difficulty of the course and how many hours you spend on it per week, and then just some open feedback if you want about how things could be improved for the course. The numerical feedback is the only thing that's required in the form, and you'll notice that this is completely anonymous, so you don't have to worry that you're somehow going to have your name or student number connected to your feedback. I have no way of tracking that, so it's mostly just to make sure that you get some ideas about how things are going. So if you can, before you get into the exercise too much, take a couple minutes and fill that in. I would very much appreciate it. And then you can move on to the first problem, which is about steady state advection and diffusion. So in this case, again, this is where we can assume that the change in temperature with time is 0, which means that any term containing a letter, lowercase t, in our equation can be ignored. And usually that also means that the math gets a bit simpler. You'll end up with an equation for calculating temperature as a function of depth. So that's what the z is here. That looks like this, and this is the equation basically that comes from the course page on solving the advection and diffusion equation. And this is what you're going to create a Python function to calculate. So you'll notice here that this allows you to calculate the temperature at any depth z in this case, assuming that you have some geothermal gradient at the surface that is a fixed value, that you know the thermal diffusivity, which is a rock property, and I think you're given values for the diffusivity to use, and then some velocity that the rock is being advected at. And otherwise, there's just a 1 minus e term here. And the equation itself is perhaps a little bit nicer than the one you deal with in the second part. So you're going to copy your intro QG functions Python file over from the earlier week's exercises, and then your task here is to make a function called steady state temp that takes the following input values. So it should be the temperature gradient, the diffusivity, the velocity, and then the depths over which you're going to calculate the temperature. So this is going to be some kind of array of values, for instance, from 0 down to some depth that is that's given to you. So you can see an example here where the depth array is going from 0 to 50 kilometers depth in 51 steps. So that's going to be every 1 kilometer you have a depth at which you're going to calculate the temperature. So you've got some tests to see if everything's working properly. Then part 2, you're going to given some values here to calculate a geotherm. So you store that as geotherm number 1. Then you make a plot of that first geotherm, adjust the values, and do the same thing a second time where you make a plot. So that's then done here. And that's kind of it for the first problem. So it's just creating a function for this steady state temperature calculation and then making a couple plots with it. Problem 2 is, my guess would be where you're going to spend most of your time in this week's exercise, and that's because you've got to convert this nasty looking thing into a Python function. It's not that bad, but I think the thing that's tricky about it is you'll have to pay attention to your parentheses because this is, as you can see, an equation where there are multiple sets of parentheses. So keeping track of which things you've got parentheses around will be probably what consumes the most time in this equation. One thing it's important to note is that this square bracket here is no different from a normal set of parentheses. It's just drawn like this to make it easier to see that it matches this guy over here on the end. So it's just a normal set of parentheses otherwise. It doesn't mean anything special. So you're given the list of what these different terms are here. So this G in this case is the initial geothermal gradient because we're calculating something that changes with time. You can see there's lowercase t in here. Otherwise, I think all the other terms are things that are in the first equation. And your first task, of course, is to convert this thing into a function called transient temp. So transient is just the word that's used to indicate that it's changing with time. So it's just another way to say something changes with time, or that it's not steady state. So you're given here your list of different inputs that should go into your function. And there's a hint here, notably, that you need to use this complementary error function that you can find from the SciPy package. And basically, if you put this at the start of your intro QG functions, then you'll have available this complementary error function that you can use inside of your function for calculating the temperature. Another note here is that you don't have to worry about converting to SI units. So the way it works out here, everything is in degrees, kilometers, and millions of years. And as it turns out, all the units cancel out nicely, so you don't have to worry about converting anything to be in meters per second or any of that stuff. So that's nice because otherwise it would be, again, a bit of work to do that. So you'll make your function, and then you've got some test cases you can run to make sure your function's working properly. You'll calculate a geotherm like you did above, and you'll get some geotherm here after 10 million years of advection with a velocity of 0.75 kilometers per million years. You'll plot it again like you did above, and then you do the same thing a second time where you put in the advection velocity, in this case of 1.5 kilometers per million years, do the same calculation and plot it. And then at the end, you make a plot where you show the two steady state geotherms and the two transient geotherms you've calculated all together on a single plot. And then there's some questions that you can answer that are optional, but useful for you to kind of think through and try to understand, because you'll see that the geotherms you get do look quite a bit different from one another. And the interesting question is perhaps why they look as different as they do. But that's pretty much it for exercise number 4. Do you have any questions about the exercise? Yeah, no question about that. But yeah, I mean, I think, again, in essence, what you end up doing once you have these two functions is making a couple plots. And so I think the amount of work you have to do in the exercise once you get the functions working is not so much, but getting the functions working, especially the second one, may take a bit of trial and error. And there'll be some useful opportunities to do some debugging with this exercise. I would like to maybe note in the GeoPython course, if you don't remember, there are some notes here in the GeoPython course in lesson number 6 about dealing with errors and debugging your Python code. So if you want, those are useful things, like dealing with errors has some useful examples of common error messages and how to understand what they're telling you. This might be useful to look at because my guess is you'll see more than a few of these kind of pink error message cells or whatever text outputs that pop up when working on the exercise. And there's also some tips here about how to do debugging. Now for us, we're not dealing with a data file, so that doesn't really apply. But this idea of making your code crash quickly and regularly, as counterintuitive as it sounds, when you're testing something, it's like the faster you can kind of test the idea, if you don't need to wait 10 minutes for your calculation to run, but to test something, try to think of ways in which you could test your functions quickly if you're having problems. and also kind of keeping track of the changes. This would be another good example where when you make a change to your function, push your changes to GitHub, and then that way if you end up breaking something later, you can always try to go back to the version that worked earlier. But just wanted to note that there's some stuff in the GeoPython course that could be helpful for working in this week's exercise. If there's not any questions, I think maybe what I'll do here is I'm trying to think of a good way to get a list of everybody who's active in the course that's here today. I don't have any paper.
One note,
yeah.
I think if I remember correctly, the GTK has some visitor day today, and some of the people might be there.
Okay.
Does anyone know, or am I hallucinating this way?
Yeah, okay. So it's right now. Yeah. Okay. How many of you are using Discord? It's pretty much everybody. So why don't we do it this? I'll just post in the channel in Discord to kind of have everybody let me know if they're active in the course. That way I have at least some place where it's documented. Also, if some of the people are away, I mean, I realize not everybody's always checking Discord, but at least maybe then there's a chance that they see the message. And also, if they're not here right now, they could post in Discord. Plus, it's just a good excuse to remind you to use Discord. So let's do it like that. So I'll just put a post there and maybe in the general channel, just ask people to kind of post in the thread to let me know who's kind of roll call of who's active. Doesn't have a Moodle, and I try to not send email just because my response rates in email are not great. So it's better that I don't risk losing messages that way. So I try to kind of keep as much of the conversation in Discord as possible, just because it's much easier to keep track of who's up to what. But anyway, I think that's kind of it for today. So you're welcome if you want to kind of stick around and get started on checking out the exercise, or if you have questions, I'll be here. There is this exponential function that you need to use this week, which I don't think we've seen. I realize now that this might be something new. So maybe if you'll bear with me for a second, I'll just open up the CSC notebooks and just show you this exponential function that you'll need for the exercise. That said, if you need to go or if you want to leave, it's totally fine to do so. But if you're interested to see this exponential function in NumPy, because you'll use it for the exercise for this week, it's quite intuitive how to use it. It works more or less like the square root function, but just so that you can see it. And make this. Okay, so if we just open up some general notebook here, and we'll do the normal import NumPy as NP thing. And why don't we go ahead and import matplotlib.pyplot as plt, so we can do a plot. So if we had some array of values like, let's make it go from, how about 0 to 100 in steps of 1.0. Or I guess with linspace, we'll do it with 101 values. So we get an array of values like this for x. So just going from 0 to 100 in steps of 1. The y value we could calculate could be done with the exponential function. So np.exp of x. So this is basically if you want to have e to some power, it's just np.exp. And then if we did the plt.plot, x comma y, we get something that looks like this, where our value goes from probably 1 up to 1 times 10 to the 43, because the exponential of 100 is a pretty big number. So that's the function that you'll need to use, is this np.exp. In this case, we're going to have something that's going to be 1 minus 1 over something in the exponential, so you'll get kind of an opposite type of curve to this one. But let's maybe make it like it doesn't really matter whether we have this go from 0 to 100 or 0 to 1. So you get a little bit less curvature here if you go from 0 to 1. But you get the idea that it is an exponential function. And let's go to 5 just to get something that shows the kind of exponential shape a bit more nicely. So that's the idea for this exercise. You'll have to use this np.exp function, and that's the way to do the e to some power. So I recommend using that. I think there is also an exponential function in the math library, but the NumPy one is a bit easier to do things like pass in a NumPy array. I think the math function will also handle array values, but I don't recall whether that's the case. I think that's the only Python thing that just came to mind when thinking of the equations. So if you need it, that's how you do the exponential function. Otherwise, yeah, like I said, that's it for today. So I'll hang out for a bit if you have questions or issues. And otherwise, same deal as always. On Friday, you can go and get some help from Levi in the exercise help sessions. But yeah, see you guys next week.